All right, today we are going way beyond just using a computer. We are going to build one from the ground up, at least conceptually. We're putting together the architect's blueprint, to really understand how these incredible machines actually think. Because what happens when you click a mouse or tap your screen? Well, it's not magic, it's a masterpiece of logic. I mean, you've got to wonder, right? A single click can launch a whole universe of activity. But here's the thing, it's not magic. And I promise by the time we're done here, you'll see this beautiful, elegant logic that connects one little keystroke to, well, the entire digital world. So where do we even start with a blueprint this massive? Well, any complex system needs a language. It needs a way to communicate. And for a computer, that language is, surprisingly, super simple. In fact, it all kicks off with just two numbers. That's it. Seriously. At the most fundamental level, everything, and I mean everything your computer does, every photo, every song, every single word, it's all just a ridiculously long sequence of ones and zeros. That's binary. It's the computer's mother tongue. But okay, how in the world do you get from a simple 1 or 0 to something complex, like the letter A? Well, the first big step was a system called ASCII. The easiest way to think about it is like a universal codebook. It gave every English letter, every number, and all the common symbols their own unique 7-digit binary code. For the very first time, we could write words in a way a computer could actually understand. It was totally revolutionary, but it had a big blind spot. It was pretty much just for English. And let's be real, the world is a big place, so we needed something bigger, something that can handle every language, from Japanese to Arabic to Cyrillic. And that's where Unicode comes in. It's the modern universal standard. It assigns a unique number to pretty much every character in existence. It's the reason we can all communicate globally on our devices today. Computers even have a really clever little trick for dealing with positive and negative numbers. They just use a single bit as a flag. If that one bit is on, the number's negative. If it's off, it's positive. We call that a signed number. But hey, if you know you're only going to need positive numbers, you can use that extra bit to represent much bigger values, and that's an unsigned number. It's such a simple but absolutely crucial detail. Okay, so our computer has a language. That's huge. But language is kind of useless if you can't do anything with it, right? So the next layer in our blueprint is giving it the power to make decisions. This is where we get into the real thinking part of the machine. The rulebook for all computer decision-making is something called Boolean algebra. And it sounds complicated, but it's really not. It's this powerful system where absolutely everything is either true, which is a 1, or false, which is a 0. And by using really basic operators like and, or, and not, computers can work through incredibly complex problems and make choices. So how is this logic physically built? Well, it all comes down to these tiny little electronic switches we call logic gates. And here's the part that just blows my mind. You only really need two types, NAND and NOR. They're called universal gates because you can build any other kind of logic, no matter how complex, just by stringing these two together. They are literally the fundamental Lego bricks of all computation. Now, when you start combining these gates, you create circuits. A combinational circuit is kind of like a simple calculator. You put some numbers in, you get an answer out. Simple. It has zero memory of what happened before. But a sequential circuit, now that's a whole different beast. Its output depends not just on what you're doing right now, but on what you did before. It has memory. And that one ability, it changes everything. So how does a circuit remember? It uses this incredibly clever device called a flip-flop. This is just a special circuit that's designed to hold on to one single bit of information, a 1 or a 0. You can flip it on or flop it off, and it just stays that way until you tell it to change. This little thing is the physical atom of information. Every single bit of your computer's active memory, it's built from millions and millions of these tiny little switches. All right, we've got language, we've got logic, and now we even have memory. What we need now is a conductor for this whole orchestra. We need the brain of the operation, the central processing unit, or as you know it, the CPU. Yeah, the CPU is the command center. Inside, you've got the arithmetic logic unit, the ALU. That's the part that does all the math and logic. You've got registers, which are like little super fast sticky notes for holding data temporarily. And most importantly, you have the control unit, which is basically the director, telling everyone else what to do and when to do it. And how does it all work? It follows this constant, relentless 3-step dance called the instruction cycle. First, it fetches an instruction.
kind of like a chef reading the next step in a recipe. Then, it decodes it, figuring out what it's supposed to do. And finally, it executes the command. Fetch, decode, execute. This simple loop happens millions, sometimes billions of times, every single second. Now, the CPU is incredibly fast, but it can't hold all the information it needs right there on its desk. For that, it relies on a really sophisticated storage system we just call memory. So let's take a look at how that's all organized. See, not all memory is created equal. The best way to picture it is like an office. Those registers we just mentioned, they're like papers sitting right on the CPU's desk. Super fast, but not much space. The cache is like the desk drawer, still really fast and close by. Your RAM? That's the big filing cabinet across the room. It holds a lot more, but it takes a second to get to. And your hard drive? That's the giant archive warehouse down the street. It's slower, but it's absolutely massive.
And this right here explains the why behind that office setup. The super fast cache is made of SRAM, which uses those same flip-flops we talked about. It's incredibly quick, but also really expensive. Your main memory, your RAM, is made of something called DRAM, which uses tiny capacitors. It's way cheaper and you can pack more of it in, but it's a little slower. It's this trade-off between speed and cost that makes each one perfect for its job.
But what happens when you run out of space in your filing cabinet, in your RAM? Well, the computer has this brilliant trick up its sleeve called virtual memory. It cleverly carves out a piece of that huge, slower hard drive and basically pretends it's extra RAM. This amazing hack lets you run these massive programs that would never normally fit. It's just an incredibly smart solution to a very physical problem. Okay, our computer has a brain, it has memory, it has logic. But it's all pretty useless if it's just trapped in a box, right? The final piece of our blueprint is figuring out how it actually talks to the outside world. This is the system for input and output, or I/O.
Now, the most basic way to do this is called programmed I/O. And here, the CPU is basically a micromanager. It's constantly nagging the keyboard. Are you ready yet? How about now? Now? I mean, it gets the job done, but it wastes almost all of the CPU's precious time just waiting around. It's super inefficient.
A much, much smarter way to do it is interrupt-driven I/O. So instead of the CPU constantly asking, the device sends a little signal, an interrupt, only when it actually has something to say. It's just like getting a text notification. The CPU can focus on other important stuff and only deals with the keyboard or mouse when it absolutely has to. So much better. But the gold standard, the best method, is direct memory access, or DMA. Think of this like hiring a dedicated delivery service. A special DMA controller handles the entire data transfer, say between your hard drive and your memory, and it completely bypasses the CPU. This frees up the CPU to do the most important job it has, thinking. And there you have it. That's our complete blueprint. We started with a simple language of ones and zeros. We built logic gates to make decisions. We designed a CPU to act as the brain, a whole memory hierarchy to store everything, and an I/O system to talk to the world. These 5 layers, this is the fundamental architecture of pretty much every computer we use today.
You know, this blueprint has served us incredibly well for half a century. But as we start pushing the boundaries with AI, with quantum computing, with chips that are designed to literally mimic the human brain, this entire structure might be about to change completely. So the real question for us to think about isn't just how computers work today, but what on earth is the blueprint for the computers of tomorrow going to look like?